Swayam Prabha. Digital India. Educated India.
Good morning all of you. Today we are going to discuss on Navier-Stokes equations and its approximations for simple flow problems. We will discuss that part. As we discussed in the last class, how we can derive the basic Bernoulli's equations from Navier-Stokes equations. That what we did it Navier-Stokes equations, from that we derive Euler equations, then we have derived Bernoulli's equations. So, that components also today I will recap it, then we will go through these today topics, which mostly I am following it the book of F.M. White fluid mechanics books for today lectures. So, you can look at the similar line of derivations in F.M. White book. So, that way let me go through the basic things what we discussed, that basically we are going to introduce velocity potentials. Okay, I will discuss more details and very interesting things, generations of rotationality, and then we will have a look at a simple solutions for incompressible viscous flow between a fixed and a moving plate. Same incompressible viscous flow we will look it for due to the pressure gradients between two fixed plates, that is acute flow what we discuss it. Then we will discuss about incompressible viscous flow in cylinders, that is what we will be discussing that. So, basically let us start with Navier-Stokes equations, which is long back, about 200 years back. So, the equations what we derive in last two classes, we will go more detail about that. Before going that, let me just write down the basics equations is the Euler equations. Okay. So, if you look at when I talk about Euler equations, you can understand it. It is for incompressibles and non-viscous or frictionless flow. So, this is the reasons we can apply it. That means, if you consider flow past a tall building, okay, a high rise buildings, okay, flow past a tall building. So, if I am looking for flow past or tall buildings, like most of the Indian cities about today we can see these tall buildings. So, if you consider a uniform stream flow, we can get in these stream lines like this. We can get a stream like this, but there will be vortex, there will be flow separations going to happen it. So, if you look at this part of the flow, okay, if you exclude the near to the structures, the flow outside of these structures, the more or less the Euler equation is valid, but near to structures, as the vorticity is there, the turbulence behaviors are there, as well as it has the flow separations, that is what is not valid for this external flow. But beyond that, you can see that the streamline patterns of this part I can always define through Euler equations, which is very basic equations, is rho dV dt, its accelerations is equal to rho g, its vectors minus grade p. That is what the Euler equations, that is what is the Euler equations, and this equation is quite valid for a flow past and tall building. The reasons what we are quantifying beyond these regions, that we can always apply Euler equations, as well as we have the derivations of the basic equations is the unsteady Bernoulli equations, also the steady Bernoulli equation, unsteady Bernoulli equations and also the steady Bernoulli equations. If you look at these equations, still we have the in Euler equations, still we have three unknowns u, v, w and p, the pressures. So, 4 unknown components are there, 3 are the scalar velocity field, 3 are the scalar velocity fields are there, which is u, v, w and the pressures, that is what the 4 unknowns are there. The basic idea comes that can you write these equations with a single scalar value. Okay, that is the simple idea comes is that instead of looking at 3 scalar velocity component, why we cannot write it with a simple scalar functions. That is what is the velocity potential function, velocity potential functions is similar to analogous to the electric field potentials and the current. So, here we look at not the current, we look at the velocity field. That means, we define it that the V can define as a scalar field of grade phi, and the phi is the velocity potential functions, phi is the velocity potential functions. Okay. So, if I define that parts, okay. So, velocity this is what velocity potential functions, okay, single functions which is have the variability functions of spaces time, functions of spaces time. Okay. It is not confined to 2 dimensional as we did for the streamlines. For the potential velocity potentials, it is a 3 dimensionals, also the unsteady part is there. Okay. So, do not be confuse yourself. So, this have the x y z, also the there is a 3 dimensional functions in x y z as well as it has a time functions. So, if I have these components, that means if I just equate it, you need not to remember line by line, do not be confused that what I can write in scalar component a very simple way. This is equal to del phi by del x I del phi by del y j del phi by del z k. So, it is just the expressions what I am putting it, just the expressions I am putting it. This is what vectors form, this is in scalar components. So, what it indicates it? It is a very simple things, u is equal to del phi by del x, v small v the scalar components del phi by del y, and w will be scalar component del phi by del z. Okay. So, for this now the velocity potential functions what you have defined it is a single functions which is having a space and the time, but using that single functions as its gradient, the partial derivative with respect to x, y and z, they are respectively representing you as u, v and w. So, instead of solving u, v, w, if I know these 5 functions, I can solve these problems. That is the idea, that instead of the 3 scalar variables, I am targeting only one variables, that is the velocity potential functions. Now, if you look at that, at which condition does it satisfy it? That is, if I define it, the velocity is a gradient of phi, phi is the velocity potential functions, at which condition does this is what justified it to us. If you look at the very basic components, if I velocity potentials, v equal to grade phi is the gradient of a scalar components will be justified, okay, or the reverse is also true, that when you have v is equal to 0. Okay. If other way around, if this is the functions, we will get it, the cross product between del and the v is equal to 0. What this means is that this condition is satisfied only these conditions when you have a irrotational flow. Okay. So, the regions where we have a irrotational flow, then those the regions we can use the velocity potential functions to define our flow fields. And the velocity potential functions what we are defining, it is a 3-dimensional components, okay, x, y, z, also it has the time component. But the conditions what we have, the flow should be the irrotational flow field, or the regions where the rotational activities merely are negligible components. Okay. So, those the regions of the fluid space we can apply the velocity potential functions. That is what will be give us advantage, instead of taking 3 scalar component of u, v, w, only the phi, the scalar components will be enough for us to solve the problem. That is the advantage, but the condition is that it should be irrotational flow. That means, if I again coming back to the same flow past a tall building, if I draw the 2 streamlines, let I draw S1, S2, 2 streamlines. If I draw those 2 streamline Sn and S2, then this is the streamlines, which is the psi functions. Okay. This is stream functions. Okay. The psi functions is a stream functions, which is defined by a constant value of C1 and C2. So, this is what we have the if you look at the velocity potential functions, okay, velocity potential functions, which we define it v is equal to grade phi. So, please look it as we derive it mathematically, and also we prove it that if this is the conditions, your del cross v, call vectors of v, that is what will be the 0, that is what it is, that irrotational flow. Okay. So, if I go for again for the same tall buildings and draw a 2 streamlines, okay, the psi equal to 1, psi equal to 2, then we can look at this is the streamline functions. Okay. So, we can have any constant value, such I substitute 1 and 2. So, you need to find out a functions which is have a orthogonality. That is what is the functions which is phi equal to C1, phi equal to C2, phi equal to 3 C3. So, this is the velocity potential functions, this is the streamline functions, this is what streamlines, both of the things we call the flow net. More details I am not going here. So, we need to draw the streamlines and the potential lines to show it that because just you interpret it, the gradient of the velocity potential functions indicates as the velocity field. That's very interesting part of here. So, you can get the velocity field if you know these velocity potential functions, but the same way if I can draw the streamlines, I can draw the velocity potential line. The only things is difference here that the stream functions exist for two dimensional cases. Okay. So, we will be drawing these flow nets, streamlines and the equipotential lines for a two dimensional irrotational flow. That is the conditions you can understand it, because stream functions need a conditions that flow should be two dimensionals and the velocity potential functions needs that the flow field should be irrotational. So, both the conditions should be satisfied to have the lines of streamlined as well as equipotential lines or velocity potential line. So, now if you look it as I drawn here, these should have a orthogonality natures. That is what we are discussing it. The streamlines and the potential lines, they will have a orthogonality each others. That means, they will have a wherever they will be cross each others, at that points they will have a 90-degree angle between them. That is the orthogonality natures of the streamlines, we will get it. Let me have a very simple way look at this relationship, the orthogonality relationship. It is not a big idea, that you take a phi functions. Okay. It is a line, let be a two dimensional functions. Okay. So, if you have a consider is phi is a constant and this line. Okay. That is what along these velocity potential functions, velocity potential functions, that what we get it that by definitions that since it is a constant. So, d phi equal to 0, and as we define it, it is a two dimensional functions, because for getting a relationship with streamlines. So, so that way if you have a d phi, that is what we will be defining d phi by dx. That is what you know it, basic chain rules. Okay, for two independent variables of dx and dy, you will get it, that is what is equal to 0. As you substitute the values, and if you want to know it, this is let be x and y. We are looking at what is a dy dx, the slope of this part. If I just rearrange it, I will get a dy by dx. Okay, that is what will be equal to minus u by v. This is for the phi equal to constant. This minus u and v, if you look at the definition of the stream functions, we can get it just reverse 1 by dy dx of the stream functions is a constant. That is what the slope of these two products, if it is minus 1, as you know it, that means two lines are interacting, meeting at 90-degree angles, or they follow orthogonality behaviors. So, this is what from basic the relationship between the streamlines and the velocity potential functions, we can get it this if you have a velocity potential function C1 and C2, and the streamlines will have a 90 degree to that. So, this is what the streamline. This is what streamline will have a psi, maybe have a C3 psi equal to the C4. So, that is the functional variability we get it for streamlines and the velocity potential functions. Many of the times when solve the equations or try to understand the flow patterns, first you draw the streamlines, and if it is a two dimensional flow, you can easily draw the velocity potential functions, which will be indicate us the velocity, how the velocity fields are varying it. That is what we can always interpret it. Now, if you look at a very interesting part, which I can relate it with very basic equations, what you know is the Newton's first law of motions. Okay, as you know it, if you look at that Newton's laws, first law of motions, okay, you know the three laws. Okay, if you can remember the first law of motions, what it says that, okay, that is the same concept what we will talk about rotationality, okay, the generations of rotationalities. Just try to understand it. What is the Newton's first law says that? Newton's first law says that a body remains at rest, or it moves at a uniform speed in a straight line, unless otherwise all balance force acts on them. Okay. So, again I have to repeat it, as if you try to understand it, if a body, okay, that is what is moving with a uniform velocity, it will move in a straight line unless otherwise there is external unbalanced force act on that. The same concept is here. The concept is same what is there in Newton's the first law of motions, which talk about when a body is moving it, if you are not given any external force, it will not be accelerator, deaccelerator, or it can change the directions of motions. The same concept is here. Instead of the laws of motions, here we talk about the rotations. That means, if the flow field is irrotational, okay, flow field is irrotational, that means, let for examples you have a uniform flows. Let us you talk about there is a uniform flow, okay, the same velocity v, the constant velocity is moving it, this exactly same law. Okay. That is what is you should correlate it, it is not much difference between fluid mechanics and solid mechanics. Here we do not visualize the body movements or object movements, you have to have a conceptually understand it. For examples, that you have a wind movements having the uniform velocities. So, when you have the uniform velocities, you will not have any, the nature of irrotationality is not change it, unless otherwise you put a object here, okay, put a object here which will create a boundary layers, okay, low viscosity zones, create the vorticities, then it will change the irrotational properties, it will go for the rotational behavior. The same concept what we call the generalized generation of rotationality. Please try to understand it, the same concept, the Newton's first laws of motions, which you could have learned it at the class 10th levels. Same concept we are looking at when you go for whether if you have a wind flow, uniform wind flow, you will have a irrotational field, unless otherwise you put a object, create a viscous stress components, as you reduce the velocity, as you get this object and the velocity reductions, those regions will be create the viscous regions, then that is the regions it will be start the rotationalities. That is what you try to understand it. Okay. That is try to understand it. Okay. That means a fluid is initially irrotational, may become rotational, okay, only if there are the 4 conditions. Okay. The first conditions is that, as I discuss it, which we can easily understand it, that if there is a significant viscous force induced by jet, wake and solid boundaries, that is what I have incorporated here, then the flow will be changed, chance goes for the rotationalities, and as it goes for rotationalities and the viscous dominance is there, we cannot use the Bernoulli equations. Okay. That is what our so popular, so familiar equations, it is no use for us when you talk about where the viscous dominance is there. So, that is what talk it here, that we cannot use these equations when you have the flow changes for rotationalities and the viscous components dominates are there. Same way if you look it, that is what is represented here. So, if you have the aerofoils like this, if you have a aerofoil and you have a uniform flow, it will be irrotational. Okay. But as soon as it touches, it creates the laminar boundary layers, below it can have a turbulent, the flow separations, and then you can have a wake flow. Okay. That is, you can just look at how the behavior is happening it. This is what subsonic levels, but in case of supersonic levels, this is what the supersonic approach, you will have a shock wave. Okay. We have a shock waves, that is what it also changes entropy gradients if you have a curved shock waves, that is what is here. Okay. That is the second conditions. First conditions, if you have a solid boundary, jack and wakes, then the flow will be changed to the rotational. Same way if you have the shock waves, because of supersonic flows, also we will have the entropy gradients, we will get it, that is what will make it flow rotationals. Okay. And if you look at that way, also we can look at whenever we have the density gradients. Okay. That is caused because of uneven heating. Okay. So, that is what it happens. Okay. So, that what will be cause the density gradients, we will get a density gradient because of stratifications, that is what because of uneven heating, or because of earth rotations, we will get it non-linear effects. So, that is the 4 conditions are necessary to change the flow field, which is initially irrotational to the rotational field. This is what is equivalent to the Newton's the first laws of motions, which talks about object motions. Here we talk about the fluid conditions changes from irrotational to the rotational field. Any questions?
Can you explain the shock waves formation again, sir?
Okay. More details I am not going here, because this course we are not talking about compressible flow, but that is the reasons I am not going detail, but if you look at in case of compressible, when you have a supersonic and compressible flow, you will get a shock wave patterns. Okay. Because anyway, the course is for undergraduate levels, I will not go to that level.
Sir, 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 in the velocity field, the part outside the obstruction, part outside the boundary, how does it react, and does the velocity profile changes outside the boundary layer?
Okay. The questions what you have, I think if I understood it, that if I have an object, okay, and I get the boundary layer formations. Okay. Just outside of the boundary layers, I will have the flow close to the frictionless flow. Okay. This is close to the frictionless. That is the reasons we will discuss in the next chapters how will be linked between boundary layers and Euler methods to solve these problems instead of looking these Navier-Stokes equation solvers. That is what we will look it, but these the reasons the outside of this part will show you the viscous is not dominant. That is the reasons we can use Euler equations to solve these problems. Or if you know the streamlines, you can just apply the Bernoulli equations to solve the problems. So, but inside this for the this is the boundary layers where we will discuss more how to link these two conditions. Instead of solving the Navier-Stokes equations, we can solve these boundary layers and the Euler equations to solve external flow field. But if you talk about any internal flow field, internal flow, for example of pipe flow, okay. So, you can understand it is totally viscous dominancy will be there. So, the here we will not have a regions which shows us the flow is irrotational, okay, because even if you have a pipe flow, it is a totally viscous dominancy is there, and the flow field these irrotationals are the rotational activities are there, okay, as vortex and formations, even if in a case of the laminar flow also. So, internal flow will not have a much Euler equations, but let me give a simple examples as you put it that concept. Many of the I think you students have solved these very basic equations to find out problems using the Bernoulli equations, that if there is a tank and there is a outlet here and it is having height h, okay, we need to compute what is the velocity here, okay. Without looking anything, we know it v is equal to square root of g h, okay. So, these are problems we could have solved in the 10th class levels or the 12th class level, but how we did it that, so we do not know it. How we apply these things if you visualize the flow field. For examples, if I draw the streamlines, okay, the flow near to the surface will be viscous dominant. The streamlines will come like this, streamlines will come like this, streamlines will come like this. Streamlines can start from here. Now, we can say that I can apply, take a streamlines, okay, take a 1 and 2, I can apply the Bernoulli equations and get it the same format, okay. The use of Bernoulli equations give me the same the relationship that V is equal to, if you look at this part, if I apply this Bernoulli equations, that means I am telling it this part, that same way I can get it V equal to rho g h, okay. Just apply the Bernoulli equation at 1 and 2. You know the velocity 0 at this point, you have a pressure is atmospheric at 1 and also pressure is atmospheric at the 2. So, that way you can just apply it, you will get it the V equal to 2 g h. But try to remember it that there is a rotational activities, viscous stress components are there. Near to the surface, you will have the boundary layer formations. Near to the surface, you will have a boundary layer formations. The boundary layer formations are there. So, using Bernoulli equations, we are just not trying to understand it, the microscopically what is happening it. We are just trying to look at a macroscopic scale that I am getting the velocities, but is it what velocity I am getting it? Is it average velocity? It is what is that? because there is a formation of boundary layers, there is a rotational activities as the fluid comes in if you take the field. So, more detail we will discuss it. That is what is objective of this course, to not to get V equal to square root of 2 G H, which it is not necessary to understand the fluid mechanics to solve these problems. But you try to understand what type of stream functions are there, and if these are the stream functions, what should be my, this could be my potential functions. Okay. This could be my potential function. This could be my potential functions. So, you should try to understand it very detailed way, how, what should be the streamlines, what will be the velocity potential functions, where we expected it, there is a formation of boundary layers because of no slip conditions of near to the structures. That what it will be retracted, that is what is here, the conditions of boundary layers will be there, and that what is will be prevailed with these 4 conditions what we are talking about. That you should remember, just for example of Newton's laws of first laws of motions, the same concept you are talking about here, that fluid is changes from irrotational to rotational if any of these 4 conditions prevails. That is the guidelines when you want to draw any streamlines, you want to draw a equipotential lines, you should know it whether these things are there or not. And second things, very easy things for us, because when you use this velocity potential functions, if I am using this velocity potential functions, then if I am using the velocity potential functions, velocity potential functions, okay, is instead of u v w the scalar components, I just use velocity potential functions, okay, and that is what will be easy for me. If you can refer to F.M. White book, even if unsteady Bernoulli equations, we can write it in terms of the phi, okay, in terms of you can write unsteady Bernoulli equations, okay, equations in terms of phi. That is not a big issue, you can just refer to that book. But what is the advantage, that when you define V equal to grade phi, okay, and your mass conservation equations or continuity equations, is that the velocity divergence, that is what is give a Laplace operator of the phi. This is what. So, basically your mass conservation equations, when you write in terms of velocity potential functions, it comes out to be a Laplace function of phi, is a linear functions, which we can easily solve it. If it's a linear functions of phi, if I getting it, okay, it's maybe the second order, but the linear functions which we can easily solve it. That is the 2 advantage we have when you write in terms of velocity potentials. Instead of solving these 3 scalar components, we define through a single functions, which is the velocity potential function. Our continuity equations becomes a Laplacian equations of Laplace equations of the phi, which is very easy to solve it, as well as we can write unsteady Bernoulli equations. That is the strength of velocity potential functions and the stream functions what we discussed earlier. I think that is what will be considered is a key points when you try to solve a many problems, complex problems. Even if you solve the problems using computational fluid dynamics tools, but always you can draw the streamlines, you can draw the equipotential lines, then you try to understand it where the behaviors or what, okay, that is what you can just look at how the behavior patterns are there. Okay. So, the stream functions are used even if the CFD solvers to understand it, the flow patterns. Now, coming back to doing some simple approximations using Navier-Stokes equations to get simple solutions of between a fixed and moving plate viscous flow. If you have, we called fluid flow. Okay. Conditions is that I have a fixed plate. Okay. So, means the velocity is 0. I have a moving plate V. I am looking at what would be the velocity distributions. Okay, I think these problems we started it first chapter of the fluid mechanics is Newton's laws of viscosity. The same concept we are talking about here. If a plate is moving with velocity v, what should be the velocity distributions, what should be the shear stress distributions, that is what we are looking at. For viscous flow, rho is there, mu is there, all are constants. To simplify the problems, we can take it, the central lines is a axis, okay. This is the x axis, this is the y directions, this will be the plus h coordinates, this is minus h, okay. And I have the plate which is moving at v, and I am trying to look at what could be the velocity distributions for viscous incompressible flow. That is my point. If you see that, what are the things we are neglecting, okay, which justified for us, like when you talk about a horizontal plate movements, so we need not to take the gravity flow. So, that means we can neglect it, okay. We can neglect the gravity component, okay. That is what is quite feasible. See, if the plates moving in horizontals, no doubt we can ignore or you can neglect this gravity flow, but just try to understand it. If I have the vertical motions, you cannot do that. So, that way you can look at how you are solving the problems. So, you have neglecting the gravity components. Second thing is that since this is a free movement of the velocity v, so you can neglect that the pressure gradient part, okay. There is no significant pressure gradient part will be there, okay. So, del phi by del x also can be neglected, okay. Another term is there, the fully developed flow. I think these things we discuss in the pipe flow, the same things I will tell it. We making the velocity v such a way that after certain times the velocity distributions are not changing, it more or less remain the same. That the conditions we call fully developed flow, fully developed flow. So, basically it should be far away from the entrance, okay. This is what because it is a long plate, so we can see that only these axial flows are there, the velocity component in y directions and the z directions both will be the 0, okay. Neglect the pressure components as the part is there. So, always when you look the problems, simplify the what are the things we can simplify, because if you look at that, Navier-Stokes equations is nonlinear equations. So, as you will have simplified it, that nonlinear partial differential equations we can convert to a simple ordinary differential equations, which we can integrate it to get the solutions. That is the strategy always. So, as a fluid mechanics specialist, always we look at which are the components are dominated, which are the flow fields we can neglect it. For examples, in this case it is only axial flow. So, on this x direction, so other components like v and w is 0, the pressure gradients are 0, since the flow in horizontal directions, the gravity components are not, it can be really neglected. So, if you look at that, these assumptions are more important as compared to substitute these components into the Navier-Stokes equations, then you get the ordinary differential equations and do a integrations, apply the boundary conditions to get the functions. That is what the steps. Now, if you look at the same components, if I look at as velocity v and I have the plate is moving like this. Okay. The first equations what we look at is the continuity equations, continuity. Okay. Velocity divergence is equal to 0, du by dx, dv by dy plus dw by dz is equal to 0. So, this is 0, this is 0. So, that means y is a only function of y is u is only functions of y, that is all. So, this is what is justified from this velocity divergence field, that as we know it that other components are 0. So, let us not consider z direction, it is a too wide. So, that means only the velocity will have a functions with respect to the u velocity components will have a along these y directions, that is what we are considering it. Now, if you apply this Navier-Stokes equations, okay, that is the part. If I look at the Navier-Stokes equations, if I apply it, if I just rewrite it here. Okay. So, starting from it is a steady flow, that is what again I am highlighting it, because it is a fully developed case. Okay. That is a steady flow. So, if you write the Navier-Stokes equations in x directions, neglecting some of the components because of steady flow and all, you will get rho u del u by del x v rho u by rho y. Z components I am not writing it because it is not having functions, minus del p by del x plus rho g x mu times of always you keep it your interpreted the things, okay, which we should make it 0. Okay, that is the idea about this strategy of Navier-Stokes equations. When you try to get analytical solutions, always your strategy is that which are the components are 0. Okay. No doubt this is already 0, we say that gravity does not matter, pressure gradient is 0, these terms are 0. Okay. So, if you look at it that way, only this terms is left it, this component is 0 as it is only y functions, that is what is from this we get it del square by u by del y square, or we can write in terms now only dy square is 0. So, you can get a functions, a linear functions with y. That's very simple things, linear functions of y. That's what you see. That's it looks very complex, that we have used nonlinear equations like Navier-Stokes equations, we use the continuity equations, but end of the day we are coming back to a simple ODE equations where we can get analytical solutions, which is having a two constants C1 and C2 are two constant, and these two constant we can get it applying these boundary conditions. As you know it, that when y equal to the minus h, the velocity is 0, the u component will be 0, y equal to plus h, the small u velocity is v. So, if you substitute these conditions, then you will get this the velocity field. That is what you will get, this velocity field. Just to I sketch it, these components, that what I am getting it after solving these problems. This is a fixed plate, this is fixed, this is the plate moving with velocity v, which is as equivalent to well known experiments is Newton's laws of viscosity experiments with a plate moving. If you look at the viscous flow, it will have a linear velocity, okay. At y equal to 0, we will have a you will have v by 2. That is what you can look at, y equal to substitute 0, you will be v by 2. So, you have a linear velocity profiles. You will have the linear velocity profiles what you get it. So, if you look at that, it is easy to get it from experiment what is necessary, but this is what the analytical solutions we get it with a series of approximations we have done it for these specific problems. Now, if you go for next problems, which is another simple problems, okay, that there is two plates are there, okay, two plates are there. It is not a pipe flow, it is a plate, okay. Just like you can see that some sort of lubricants are moving it within a two plates, okay. Both are the fixed, but they are flow is moving because of the pressure gradient, and as the pressure decreases, the flow is moving because of the pressure gradient. Due to the pressure gradient, the flow is moving. That part we are looking at for a incompressibles and the viscous flow, rho and mu constants, and the same coordinating systems like x, y, minus h and plus h. We try to solve it, what should be the velocity field. Okay. So, in this case both the plates are fixed, the flow is happening due to the pressure gradient. What should be the velocity field? Okay. So, if you look at that same way, if you can approximate it, okay, you will get it the very basic things that in x momentum equations, okay. I am not deriving step by steps, you always can follow this FM White book to get it like last examples what I did it, cancelling out all the terms which is which are the 0. The same way if I do it, I will get this part, okay. That means I will get mu del square u by del y square is equal to minus grade p by grade x. Okay. So, this is what the x momentum equations. If I apply for y and z momentum equations where the v and w is 0, the same conditions. Here v, w's all are 0 values, okay. It is only the axial flow, it is happening it, okay. So, because of that you will have a dp by partial derivative of p in a y and z directions will be 0. So, looking this p is only a function of x only, that is all, as p is only a function variabilities and the x directions, that is what indicating here. If I substitutes that, okay, there is a few of the steps we have not discussed line by line. If I substitute that and dp by dx is a, if I consider is a constant, okay, and then if I just look at the solutions of these conditions, we will get it the u is a functions of the gradient and y square y and the c1 c2 two constants are there. So, if you look at these two constants also I can get it, because when y equal to minus h, here the u velocity is equal to 0. At this point when y equal to the plus h, the u is equal to 0. Okay. So, if you substitute that, you will get a c1 and c2 values So, you will get a paraboloid functions, okay, which is similar to the pipe flow. Here I am talking about flow through the plates. We are getting this the flow patterns which comes like this, and always you can find out what will be the u maximum here. That is what you can get it, just substitute y equal to 0. You can get the u maximum, and you can just integrate the u, the velocity functions, okay, from minus h to the plus h d y into length, okay, which is a unit value. You can get the discharge. We can get the discharge. You see, if I know the velocities, if you just integrated what this and the unit value, if I consider the perpendicular to this plane, that is what I will get the discharge. So, same way, if I know the velocity distributions, also I can get the wall shear stress. I can get the wall shear stress. Those are examples we have, but today let us complete this part with this derivation. Thank you.